periodic table, it is about the classification of elements and trends in properties. Why do we need to classify elements at all? Suppose if you happen to know that lithium, sodium, potassium, rubidium, all of them belong to the same group, you can easily understand the relation in their properties. You can say if the formula of lithium chloride is LiCl, that of sodium chloride will be NaCl, KCl or BCl. So, all elements with similar properties have been arranged in horizontal and vertical lines, and the horizontal lines are called periods and the vertical are called groups. Look here, we have 18 groups in the periodic table. This is the broad picture of the periodic table. 1s, 2s, 2p, 3s, 3p, 4s, 4p, 5s, 5p, 6s, 6p, 7s, 7p. Every period starts with an S element and ends with a P element. And after 4s, we will get 3D and followed by, after 4s there is a twist, 3D, 4D, 5D, 6D. And after 6s, you have 4f and 5f. If you closely observe, this is the arrangement of elements in the periodic table, and this of course is the electronic configuration, the above principle and the Moyle's diagram. So, if the last element, if the last electron enters S sublevel, it is called S block. For example, look at the electronic configuration of sodium: 1s2, 2s2, 2p6, 3s1. Therefore, the last electron, which is called the differentiating electron is in S, therefore it is an S block element. And first group of S block, not only an S block, first group of S block, 3s1. So, if you happen to know the electronic configuration of a particular element, you can identify its position in the periodic table. So, now tell me 3s2, 3p3, an element whose valence shell configuration is this, of course followed by 1s2, 2s2, 2p6, 3s2, 3p3. Where do you find this element? 3p. You will find that in the third period, 3p. And p block, the 6 elements towards the extreme right are called p block elements. Why do we have 6 elements only there? Because P sublevel can accommodate 6 electrons. You can have P1, P2, P3, P4, P5, P6. And we have only 2 groups in the S block because S sublevel can accommodate 2 electrons only. S1, S2. Sodium, magnesium, S1, S2. Like that, the D block will have 10 groups because the D sublevel can accommodate 10 electrons, D1 to D10. And of course, these F block elements are written separately because if you write the 14 elements of F block here, it will be too lengthy, 32 groups. Therefore, the 14 elements are written separately. So, what is the definition of a particular block? If the differentiating electron, what do you mean by differentiating electron? Last electron. The last electron enters S sublevel, it is an S block element. P sublevel P block, D sublevel D block, F sublevel F block. Okay? The last electron enters a particular sublevel. The block will be decided basing on that. I will write the electronic configuration of an element and let us see how to find out which block that belongs. 1s2, 2s2, 2p6, 3s2, 3p6. You know after 3p it is 4s, 3p6 and then 4s2, 3d3. Where do you find this element? You will find this in the D block, because the last electron, look at the last entering electron, the electron that has entered last is in D sublevel, therefore this belongs to D block. And which period you will find this? Since 3D comes only after 4s, as I have already told you, 1s, 2s, 2p, and the trend continues like that: 3s, 3p, 4s, 4p, 5s, 5p, 6s, 6p, 7s, 7p. But after 4s, 3s, 3p, after 4s you get 3d and of course 4p. Therefore, this element belongs to the fourth period. Though the last electron is 3d, 3d comes only after 4s according to Abo principle. Therefore, 4s to 3d3. You will find this element, the D block, the third group of D block. What are the 18 group numbers which were given earlier by Mendeleev? These are the 18 groups: 1a, 2a. The first two groups, 1a, 2a, which belong to the S block. 1a, 2a belong to the S block. 3b, 4b, 5b, 6b, 7b. 3b to 7b, followed by all three are 8 groups, 8, 8, 8. The old 8th group, and 1b, 2b. And 3a, 4a, 5a, 6a, 7a, and the last group it is designated as 0. All these designations come from Mendeleev's classification. So, you have 2 groups here and you have 10 groups here: 3b, 3b, 4b, 5b, 6b, 7b, 8, 8, 8, 1b, 2b, and this is called D block. D block. And you have 3a, 4a, 5a, 6a, 7a. This is called the P block. So, you need not memorize anything. P sublevel accommodates 6 electrons, therefore P block has 6 groups. D sublevel can accommodate 10 electrons, therefore D block has 10 groups. So, this is D1, D2, D3. Of course, there is some variation in chromium, in the electronic configuration of chromium, like this 10 groups. So, just observe the rhythm here: 1, 2, 3, 4, 5, 6, 7. Whether they are A or B, they are 1 to 7. 1 to 7, 8, 8, 8, and 1 to 7 again. Of course, these two are B and they are A's. So, 1, 2, 3, 4, 5, 6, 7, 8, 8, 8, 1, 2, 3, 4, 5, 6, 7, 0. The 18 groups. The IUPAC has given 1 to 18 numbers. Group 1 is 1, 1, 2, like this: 1, 2, 3 to 7, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 to 17 and 18. This is the IUPAC designation. Okay. Now, as a block of elements, if you observe the S block and the D block, P block, of course, F block is given at the end. For some reason, we will discuss it later. But as of now, suppose nitrogen, phosphorus, arsenic, antimony, bismuth. All these belong to the same group of the periodic table. They belong to the group 5A, the new 15th group. 15th group. Now, if the atomic number of nitrogen is 7, how to find the other atomic numbers just from the first one, 7? Okay, there is a simple rule suggesting this. Look here. Between 2 and 12, both inclusive, greater than 12, less than 39, you divide it into 3 ranges: less than or equal to 12, greater than 39. You add 8 here, 18 here, and 32 here. Now, so 7 is in the first range, add 8 to it to get 15. 15 plus 18, 33. 33 plus 18, 51. 51 plus 32, 83. Once again, 7 is less than or equal to 12. When it is less than or equal to 12, add 8. And greater than 12, less than 39, 15. 15 is here, between 12 and 39. Add 18. And 33 is once again in this range, 12 to 39, add 33. 51 is greater than 30, lost range, so add 32 to get 83. Like this, just by following this simple principle, you can write the numbers. And let me start with 1, which is hydrogen, the first element. 1. 2 is the last of the first period. We have only 2 elements in the first period, hydrogen and helium. And what will be the other numbers? 3. And proceed to write the remaining. 3 plus 8, 11. Because 3 is in this range. Less than 12, add 8, 19. 19 is between 12 and 39 in here, 19. Add 18 to get 37. 37 is again here, 37 plus 18, 55. 55 plus 32, 87. So, if you follow this rule, you will find which element resembles which other elements in properties. Suppose if I just ask 25, the properties of 25 and atomic number 25, manganese, plus 18, 43, technetium, 43 plus 32, 75. All these 3 elements will have same properties. Manganese, technetium, rhenium. Of course, you need not remember these names, only manganese only. So, if you just add the relevant difference, you will get to know which element resembles which. Now, let us complete the table. The first period contains just 1 and 2, 3. What will be the last? 2, add 8 to get 10. 3 to 10. Helium, neon. This is hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. This is helium, neon. 11 to 10, add 8 to get 18. 18 is in the second range between 12 and 39. In this range, 18 is here. 18, add 18 again to get 36. 36. 37 to 36 is again less than 39. Add 18 to get 54. 86. 118. So, helium, neon, argon, krypton, xenon, radon, and this is called unoctium. 118 is unoctium. 118. So, the first period, the horizontal line, the horizontal row contains just 2 elements. Second period, 8 elements, 3 to 10. So, lithium to neon, sodium to argon. So, if you just remember the first group and the last group, you will be at least broadly able to describe the periodic table. If I ask you something about the fourth period, you can say, sir, it starts with potassium and ends with krypton. Potassium to krypton, and 19 to 36 you have 18 elements. So, first period has just 2 elements. Second and third periods, they have 8 elements. These two have 18 elements, and this one has 32 elements, cesium. And this, of course, all the elements between 87 and 118 are not discovered. 1 or 2 are still to be discovered. Okay. It is incomplete. First period is the shortest period with just 2 elements. Second and third periods are short. You just have 8 elements from lithium to neon. Third period also is a short period. Shortest, short, long period, longest period, and incomplete. First period is the shortest. These two are short, these two are long, and this is the longest with 32 elements. And the last period. So the simple rule, remember 12 and 39 are significant numbers in chemistry. 12 less than or equal to 12, greater than or equal to 39. You need to add 8, 18, 32. Now, what are the noble gases? Helium, neon, argon, krypton, helium, neon, argon, krypton, xenon, radon. 54, 86. They are at the last of the periodic table, as you know well. They are at the last. So if I give you a particular atomic number, you will be able to say which block that belongs to. Noble gas atomic number +1 +2. Add 1 or 2 to noble gas. Noble gas +1 +2, they belong to S block. And noble gas atomic number -0, -1, -2, -3, -4, -5, P block. And 58 to 81 and 90 to 103, they belong to F block. They are called lanthanides and actinides. This 4F series is called lanthanides. 5F series is called, means the last electron entering 4F and the last electron entering 5F, that is called F block. Now, so all others belong to D block. All others belong to D block. So, the element number 33 belongs to 33. How close is this to noble gas? 36 minus 3. 3 less than. So, it is in the P block. 36 minus 3, P block. 33 belongs to P block. And which period? You know krypton is in the 4th period, therefore this is in the 4th period. And 88 belongs to, 33 belongs to P block, and 88 belongs to 88. 86 plus 2. You must see how close is an element to the noble gas. So 86 plus 2, S block. And if it is 65, 65 means 58 to 71, 58 to 71, 58 to 71, that is 4F series, lanthanide. So, all others belong to D block. Just looking at how close a particular element to the noble gas atomic number, you can decide. Now, periodic properties. Predictable properties. Properties that you can predict. At least you should be able to predict the trend in properties. Suppose if I say the radius of lithium is X, what can you say? What must be able to say about sodium? You must be able to say it is greater than X. Because top to bottom in a group, the size increases, small, because you have just 2 orbits here, 1s2, 2s1, you have 2 orbits, and you have 3 orbits here, 1s2, 2s2, 2p6, 3s1. So you have 3 orbits. So as the number of orbits increase, the size increases. It's common sense. So it's only the number. So this is atomic radius is a predictable property, and it is a periodic property. So what are periodic properties which we can predict? Predictable properties. Now, let us look at the trends in some of the periodic properties. Atomic radius. Atomic radius. Left to right in a left to right in a, let us first discuss top to bottom in a group. Top to bottom in a group, what happens to atomic radius? Top to bottom in a group, the trends in atomic radius. Lithium 2 1, distribution of electrons in the main levels. The total atomic number of lithium is 3, 2 in the first orbit, 1 in the second orbit. Sodium 2 8 1, 2 orbits, 3 orbits. So top to bottom, what is happening? More orbits, more size. As the number of orbits is increasing, more orbits, more size. So what is our conclusion? Top to bottom in a group, the atomic size increases. Lithium, sodium, potassium, like this. As you go down a group, the size increases. What about left to right in a period? Case 2. Left to right in a period. Left to right in a period. Sodium 281, magnesium 282, aluminium 283. We know all these three belong to the third period with atomic numbers 11, 12, 13. 11 protons, 12 protons, 13 protons. So left to right, what is happening? The number of orbits is the same. 3 orbits, 3 orbits, 3 orbits, 3 orbits, 3 orbits, 3 orbits. So though the number of orbits remain the same, size decreases. That is a peculiarity. Why? The nuclear attraction is more. You have 11 protons only in the case of sodium, 11 protons attracting 1 electron, and here 12 protons attracting 2 electrons. So though the number of orbits is the same, size decreases because of increased nuclear attraction. So top to bottom in a group, size increases, left to right, size decreases. So atomic size depends on number of orbits and atomic radius depends on number of orbits. 2. Nuclear charge. The number of protons in the nucleus, greater the number of protons in the nucleus, greater will be the nuclear pull, and therefore size decreases. Sodium, magnesium, left to right, number 11, 12, 13 atomic numbers like that. Aluminium. Now, case 3. Left to right in the series of D block. D block, like scandium, titanium, vanadium, all of them belong to the 3D series. Atomic number 21, 22, 23, 24, scandium, titanium, vanadium, like that. So there are some minor variations here. Scandium, atomic number 21, 21 protons, 22 protons in the nucleus. 3D1 4s2, 3D2 4s2, 3D1 4s2, 3D2 4s2. So here both of them have 4 orbits. Both scandium and titanium have 4 orbits only. Therefore nuclear charge should matter, and nuclear charge does matter. 21 protons, 4th orbit, this is the 4th orbit, and this is about scandium. 22 protons, once again 4th orbit. There are 2 electrons in the 4th orbit. These are the electrons I am referring to. 4th orbit. So, actually they have same orbits, therefore they should have same size. But no, greater nuclear attraction, therefore it should be smaller. But there is one more difference. Orbits is same, nuclear charge is more, but there is another factor we have to consider here, that is the number of inner electrons. You have 1 electron in the d sublevel, 3d, and 2 electrons in here. So the number of inner electrons is increasing, 1, 2. So what do? The inner electrons repel the outer electrons. There will be repulsion between electrons and electrons, which is called screening effect or shielding effect. This nucleus, of course, being positive, the nucleus always tries to attract the electrons, but electrons in the shells before you, there will be repulsion between these two. No doubt there is nuclear attraction, but there is electronic repulsion also, which is called screening effect or shielding effect. Therefore, what happens due to greater shielding effect? When compared to scandium, you have 2 electrons pushing it away. You have only 1 electron here, you have 2 electrons repelling. Therefore, a little more screening in titanium, their sizes do not decrease significantly. Top to bottom, sizes increase, left to right, sizes decrease, but in series of D block, sizes do not decrease significantly, and there are some other variations across D block. We need not go into those details right now. So what is the conclusion? Sizes, atomic radius do not decrease, they decrease, but they do not decrease significantly due to repulsion from inner electrons, which is called screening effect or shielding effect. Screening or shielding effect. So, size factors affecting radius. One of them is number of orbits, more orbits, more size, nuclear attraction, more nuclear attraction, less size, and shielding effect. Shielding effect. The inner electrons, nucleus tries to bring in the electrons, outer nucleus tries to bring in the outer electrons, but the inner electrons will try to push them away. Now, so top to bottom in groups with some variations, 1 or 2 variations can be there, but we are looking broadly, the broad picture of the periodic properties. We are not going to discuss individual differences. Left to right in series of S and P block, where you have S and P elements only, that is the second and third periods, where you strictly have S and P elements. There is no reference to D in the second and third period, because D starts only in, in sizes do not decrease significantly. They are decreasing, you can see they are steadily decreasing here, but here in D block, sizes do not decrease significantly. So, what is the essential difference between S block, P block elements and D block elements? The progressive electron, suppose look at the configuration of aluminum 3s2 3p1, aluminum, silicon 3s2 3p2. So, the last electron is entering the same level, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. So, the last electron coming and sitting in the last level, they are called representative elements. Okay, but observe Scandium, titanium, the progression in scandium, titanium, vanadium, etc. It is 3d1 4s2, 3d2 4s2, 3d3 4s2. So the last electron is not going to the last orbit, like the last coming student not going to the last bench, he is coming and sitting in the last but one bench. There is no rule that the last coming student, the last student, everybody came to the class, there is one student yet to come, last student is coming. There is no rule that he should sit in the last bench only. He may come and sit here also if there is a vacancy. So last electron entering last level, they are called representative elements. Let us illustrate it that way. Last coming electron, which is called differentiating electron, the electron that is to come last. All electrons have come, only one electron is still to come. Suppose in 23, after 22 electrons are filled, the 23rd electron is the last electron. Last electron enters last level or ultimate last shell. They are called representative elements. Representative elements. The last electron entering last but one level, they are called transition elements. The last electron entering last but one, that is called, let me put one more orbit for safe side. Last electron entering last but two level, they are called inner transition elements. Inner transition elements. So look at the definition. Last electron, where it is coming? Last electron coming to the last level, which is called ultimate. Ultimate. Penultimate, anti-penultimate. The last but one, last but two. Nth orbit, n minus 1, n minus 2. So there will be difference in properties depending on where the last electron come. How well the last valence electrons in the last shell, how well they are shielded depends on where the last electrons are coming and sitting. Now, left to right in series of F block, which are lanthanides and actinides. Cerium, atomic number 58. From 58 to 71, they are called lanthanides, all 14 elements put together. And praseodymium, 59, 58 protons, 59 protons. The electronic configuration of cerium is 4f2, 6s2. How to remember this? Very simple. 1s, 2s, 2p, 3s, 3p, 4s, 4p, 5s, 5p, 6s, 6p. So, with the completion of 1s, the atomic number is 2. With the completion of 1s. With the completion of 2p, 6, the atomic number will be 10, helium, neon. 18, 36, 54. So, I am talking about the electronic configuration of 58. 58 means 54 electrons are over. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So, 54 electrons have been filled up. 6s2, 56. This is 54. With the completion of 5p, it is 54. With the completion of 6s, this is 56. So the next last two electrons, 4f2. So where is the last electron coming? The last electron is not going to 6th level. The last electron is not going to 5th level. Moreover, the last electron is going to last but one level, inner transition. Okay. So you learn the electronic configurations. 59, 4f3, 6s2. So what is our expectation relating to sizes? 6s2, 6s2. Same orbits, same size. This has 6 orbits. 6 orbits. This also has 6 orbits. Shall I say same orbits, same size, cerium and praseodymium, 58, 59, 6 orbits, 6. 58 protons, 2 inner f electrons. Here you have 3 inner f electrons. 59 protons. Look here. Let us start with the first argument. Same orbits, same size. No. More protons, more nuclear attraction, more protons, more. I am comparing 58 and 59. Same orbit, same size. No. More protons, less size. Perhaps. But there are 2 inner f electrons here, 3 inner f electrons. What is it we expect? Since the inner electrons are more, they may be repelling the outer electrons. But the thing is, the f electrons do not shield properly. 4f cannot show any effect on 6s or less effect. Therefore, here once again the nuclear charge wins. Okay? So, though inner electrons are more, so what is our conclusion? Though the number of inner electrons is increasing due to their poor shielding effect, f electrons cannot shield properly, sizes decrease, and this is called lanthanide contraction. Lanthanide contraction. So, more inner electrons, but they are not showing any effect. In the case of D block, at least they are showing some effect. In the case of F block, the inner electrons do not show much effect. Therefore, sizes decrease once again. Both in lanthanides and actinides, you can call it actinoid contraction if you want. So, that is the story of atomic radius. So, second factor that can be predicted across a period and down a group is ionization potential or ionization energy. What is ionization potential or ionization energy? The energy required to remove an electron from the outermost shell of a neutral gaseous atom in its ground state. Suppose here is an electron, the outermost shell, the last electron. The electron is attracted by the nucleus. I have to remove the electron, for which I have to give energy. I have to force the electron out. It doesn't come out automatically. I have to remove it using force. And the energy required to remove the electron is called ionization energy. If it is electric potential, it is called ionization potential. That is, if you are using electricity, it is called ionization potential. Otherwise, it is ionization energy. How can you remove an electron? You can heat it, or you can apply a voltage. In that voltage, the electron may come out. So, the energy required to remove an electron from the outermost shell of a neutral gaseous atom in its ground state. There are so many conditions like outermost shell, neutral, gaseous, ground, because to bring in uniformity, whenever two persons calculate, they should start with the same and end with the same. And this is what is expected. You should start with X in gaseous state, and the X should be in its ground state, and this is not ion, you see, this is X, this is an atom, and this is in gaseous state, and the X is in ground state, means the electron is in its ground state. It is not given any energy already. So, now you have to give energy and convert that to X plus in gaseous state. The energy required is called ionization energy. In general, ionization energy is inversely proportional to size. As the size increases, IP decreases. And of course, because bigger the atom, lithium is a small atom, the electron is close to the nucleus. Sodium being a big atom, it is away, therefore it can be removed easily. So as the size increases, IP decreases. And whatever factors affected size, you can conclude from size only. The screening also affects size and thus affects ionization potential, the screening effect, which pushes the outermost electrons. Here I am trying to remove the electron. If the inner electrons try to push the electron away, my job is made easy. The inner electrons are pushing, means I am trying to remove and they are helping me. Therefore, a little energy is required. Now, so what is it we can conclude? In general, top to bottom in a group, top to bottom, as the size increases, IP decreases. IP decreases. There are some variations in some groups. Let us be too particular. We have to learn in a broader way to start with. Then we can go to finer aspects. IP decreases. Left to right in a period, the sizes decrease and the IP also decreases with some corrections. Lithium, beryllium, boron. Look here. Beryllium and boron. (1s2) 2s2. Boron 1s2 2s2 2p1. So beryllium is bigger, boron being the next element in that period smaller, left to right sizes decrease. So we expect the IP of boron to be more, but because beryllium, the electron, the outermost electron is a paired electron, paired, and here is an unpaired electron. Therefore, completely filled, half-filled sublevels, they stabilize the atom. The electron cannot be removed more easily. Therefore, beryllium and boron, the IP of beryllium is more even though the size decreases. So, what is the conclusion? Completely filled sublevels half-filled sublevels. Provide stable electronic configuration. Stable in the sense you will not be able to remove the electron easily, stable electronic configuration. So what happens as a result? Their ionization potentials are greater than their neighbors. Don't tell me that the IP of beryllium is greater than everybody. Just the IP of beryllium is greater than that of boron just because of its half-filled configuration. So, the elements of 2A and 5A, you look at nitrogen and oxygen, nitrogen, the next element oxygen, smaller in size, 2s2 2p3, and this is 2s2 2p4. So, this is a stable electronic configuration because of its half-filled 2p3, half-filled configuration. And 2p4, why do you say it is half-filled? The p sublevel can accommodate 6 electrons, you have p3. So, p6, p3, they contribute to the stability. Therefore, the IP of nitrogen, though nitrogen is bigger, what is the factor we are giving emphasis on? Oxygen is smaller, its IP should have been more. But though nitrogen is bigger than oxygen, the IP is more because of its half-filled configuration. I once again repeat, between nitrogen and oxygen, only this applies. You should not apply the same logic to fluorine. You should not say half-filled configuration, fluorine doesn't have half-filled. So, only when compared to their neighboring elements, nitrogen, oxygen only, don't extend the logic to fluorine. Fluorine once again size. So, what matters is size with some minor variations. What matters is size. So, the IP of lithium less than boron, less than beryllium, IP of less than carbon, less than nitrogen, less than oxygen, less than fluorine. But look here, once again you have actually this should be the order: lithium, beryllium. This is what we would have liked to have, means depending on sizes, this is the expected order. Group 1, 1, 2, 3, 4, 5, 6. It is easy to remember. 1 less than 2 less than 3 less than 4 less than 5 less than 6 less than 7. It would have been better to say in a steady manner: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. But in beryllium and boron and nitrogen and oxygen, there are variations. So now just remember the 2A elements and 5A elements, there can be some individual differences with 2A and 5A. Elements of 2A compared to 2A, 3A, 5A, 6A, there is an anomaly here. So what is the correct order? Lithium less than boron, less than beryllium, less than carbon, less than oxygen, less than nitrogen, and oxygen, nitrogen, less than fluorine. So it is 1, 2, 3, 4, 5, 6, 7 only, with some minor variations in beryllium, boron, nitrogen, oxygen. Due to half filled in the case of nitrogen and completely filled in the case of beryllium. Half filled configuration S2P3, and this one is S2. Electron gain enthalpy. Electron gain enthalpy, del EGH, electron gain enthalpy. The old term for this is electron affinity. It was in the past called electron affinity. It is the desire for electron. Affinity means desire, how strongly an atom wants an electron, electron affinity. So when an electron is added to the nucleus, when a new electron from outside is added to the nucleus, energy is released. Why? You already have an atom here and you are bringing an electron from infinite distance. Adding an electron means bringing it from somewhere, electron from infinite distance, and you are bringing electron from the infinite distance to the nth orbit. So it's like electron jumping from a higher level to lower level. Therefore energy is released, as simple as that. What do you mean by adding an electron? Adding an electron means bringing an electron from infinite distance. Adding an electron. Bringing the electron from infinite orbit to the nth orbit. Infinite orbit to the nth orbit. So when the electron jumps from a higher level to lower level, energy is released. Therefore electron gain enthalpy, we can easily define that way. The energy released when an electron is added to the outermost shell of a neutral gaseous atom in its ground state. Once again the same rules apply. The atom should be neutral, it should be in its ground state, and an electron is added to the outermost shell only. So X in gaseous state is added an electron, X becomes uni-negative anion, X minus gaseous state. X in gaseous state. The energy released or absorbed. Enthalpy always means energy released or absorbed. You need not always say energy is released. It's an old habit to say energy is always released, but sometimes it may be absorbed also. Try and imagine giving an electron to helium. Will helium take an electron? Helium will reject the electron. You have to force the electron into helium. It has a stable configuration and it doesn't want any more electrons. If you want to give it an electron, you have to force the electron, which is called, you have to use energy, you have to give energy. Their energy is not released. But with others, like chlorine, if you give an electron, it becomes too happy, it becomes Cl minus, and therefore it will be too happy. therefore energy is released. Whereas helium doesn't want an electron, but you are forcing an electron. Now, similarly, in general, electron affinity is inversely proportional to size. Electron affinity is inversely proportional to size. Means the energy release will be, you compare chlorine and bromine, bigger in size, an electron is coming from an infinite distance to the nth orbit and nth orbit. And the outermost orbit of chlorine is 3 and that of bromine is 4. You know, chlorine has 3 orbits and bromine has 4 orbits. Where is the electron coming from? Electron is coming from infinite orbit to the third orbit, to the third floor of a building, and infinite to the fourth floor. So more work is done here, therefore more energy is released. So in general, electron affinity is smaller the atom, more energy is released. The thermodynamic terms, it is more negative, more energy is released. Now, but it is an exception for the first member. In a group, from first member to second member, energy, fluorine, look here, the electron gain enthalpy of chlorine is more. Means I am talking about the released energy. I am not talking about the sign convention. I am not talking about more negative, less negative. More energy is released in chlorine. Why? Though fluorine is smaller than chlorine as compared to fluorine, bromine. Fluorine, chlorine, bromine. The electron is coming from infinite distance to second orbit, third orbit, fourth orbit. Earlier, I deliberately compared chlorine and bromine only. I was not talking about fluorine. Now also, electron going to chlorine, that is third floor, fourth floor, more work is done here, more energy is released. By the same yardstick, fluorine, the electron is doing more, traveling more distance, jumping to. So what should have happened? Here more energy should have been released. But that is true. Smaller the size, greater the energy released. But in the case of fluorine and chlorine, what happens is, fluorine being too small, the incoming electron faces greater repulsion. 1, 2, 3, 4, 5, 6, 7. Okay. Already fluorine has 7 electrons in its outermost shell, and the incoming electron faces some repulsion, and thus lesser energy is released when compared to chlorine. Chlorine also has 7 electrons, but that being a big atom, the incoming electron doesn't face as much repulsion as it does in the case of chlorine. You see, so too many electrons in too little space is the case with fluorine. Here, chlorine being a big atom, it faces less repulsion. Okay? Therefore, in general, smaller atoms, greater energy is released, and from 5A to 7A, group 5A to 7A, starting with 5A to 7A, less for second member or more for second member, means the electron gain enthalpy of fluorine is less than that of chlorine and bromine, iodine, like this. So second member has high electron affinity. Now let us answer a few questions on what we have studied. Fluorine, chlorine, bromine, iodine, which has the highest electron affinity? As per the rule, small atom should have more electron affinity, more energy must have been released in fluorine, but being more for a second member, element with highest electron affinity is chlorine. And fluorine, chlorine, bromine, iodine, highest ionization potential among these four, among fluorine, chlorine, bromine, iodine, highest ionization potential. Who has highest ionization potential? Fluorine being the first one and the smallest one. Fluorine is smaller, chlorine bigger. Top to bottom, what is it we discussed? Fluorine is the smallest, therefore most IP, and electron affinity should also have been less, but due to greater repulsion, so highest IP is possessed by fluorine among these four. And highest electron affinity, who has highest electron affinity? Chlorine. This position also must have been won by fluorine, but because of its too small a size, chlorine. Then smallest in size, smallest one is of course fluorine. Now sodium, magnesium, aluminium, among these three, highest IP, highest ionization potential, sodium, magnesium, aluminium. First group, second group, third group. When it comes to sizes, sodium is the biggest, magnesium is smaller, and aluminium is the smallest among these three. But though aluminium is smaller than magnesium, because of half filled configuration, 3s2 here, 3s2, 3p1 here, highest IP is possessed by magnesium only. Highest IP is for magnesium only. Now I1, I2, I3, I4, they are the successive ionization potentials. First IP, energy required to remove the first electron, energy required to remove the second electron, third, fourth. What happens? It is easy to remove the first electron, but more difficult to remove the second, third. That is, when one electron is removed, X becomes X plus, it is already positive. And to make it X double plus, di positive, it will be more difficult and more difficult, because as you go on removing the electrons, the number of protons goes on increasing. Here 1 electron less, here 2 electrons less, here 3 electrons. Therefore, it is easy to remove the first electron when compared to the second electron, I1, I2, I3, I4. And there is one interesting question here. Suppose the four successive IPs of an element are 100, 200, 300, successive ionization potentials. What do you mean by that? Energy required to remove the first electron, the second electron, the third electron, and fourth electron, like this. What does it tell you? First electron, it is sold rather easily, 100. Second, 200, okay. Third, 300. But when it comes to fourth electron, the atom is demanding a lot of energy, 5,000. Means first 3 electrons are sold relatively cheaply, but look at this very costly electron, 5,000. So what does it mean? What does it mean? After 3 electrons are removed, the nucleus is attaining stability, the atom is attaining stability. First 3 electrons, 100, 200, 300, okay. But the fourth electron seems to be very precious for the atom. Which elements will behave like that? Fourth electron being very precious, maybe that must be a third group element. For example, aluminium, 1s2, 2s2, 3s2, 3p1. So 2, 2s2, 2p6, 2, 8, 3. What does it mean? Aluminium has 3 electrons in its outermost shell. First electron, okay, take it. Second electron, 1 electron, okay. One more, okay. One more, okay. But after 3, it is getting noble gas configuration. So it is rejecting to give the fourth electron, though it is giving 3 electrons rather easily, but the fourth. So look, when there is a sudden large jump, whenever there is a sudden large jump in ionization potential, you can predict the group. Okay? After 3 electrons, the fourth electron has been very difficult to be attained. That is it. Until now, we have discussed trends in ionization potential, atomic radius, atomic radius, ionization potential, and electron affinity. Now let us look at more trends, more periodic properties. Look here. We can broadly let this be the periodic table. Elements towards the left side of the periodic table, towards the left you just put a plus, and towards the right you put a minus, and a minus above, a plus below. What does it tell you? Plus, minus, minus, plus. Elements towards the left side of the periodic table are more electropositive. What do you mean by electropositivity? The readiness to lose electrons. If I ask you an electron, you should be able to give it to me immediately. The readiness to lose electrons. Electropositivity. The readiness to lose electrons. So, towards the left side, you have group 1, group 2, group 3, group 4, etc. So, all of them have 1 or 2 electrons only in the outermost shell. What do you mean by group 1? It has only 1 electron in the outermost shell. Second group means 2 valence electrons. So, in fact, valence electrons is equal to group number, or vice versa. Group number is the valence electrons, except of course in 0 group. So, when you have 1 or 2 electrons only in the valence shell, like in the case of sodium 281, what will it do? It has got a useless electron in the outermost shell, so it will be very ready to part with the electron. So, electropositivity means the readiness to lose electrons. So, towards the left side of the periodic table, elements are more electropositive. More electropositive. Look at the comparative degree. When I say more electropositive, they are more electropositive on the elements towards the right side. Now, more metallic. Metallic nature is precisely that only, the readiness to lose electrons. If you are ready to lose electrons, you have got metallic properties. Now, better reducing agents. Reducing agent. One who gives electrons. You just stick to this definition only when it comes to oxidation and reduction. Don't learn too many definitions. Stick to this. One who gives electrons is called a reducing agent, and of course the opposites are opposite. Don't tell me one who takes electrons is an oxidizing agent. That goes without saying. Reducing agent is one who gives electrons. So, towards the left side, they are ready to give electrons. They are better reducing agents. They give electrons to others. They are ready to lose it. And their oxides are more basic. Oxides are more basic, of course, when compared to the right side. Oxides are more basic, more electropositive, more metallic, better reducing agents, and oxides are more basic. And you can just imagine the opposites: more electronegative, more non-metallic, and better oxidizing agents. And their oxides are more acidic. So, elements towards the top of the periodic table, they are minus. Minus means all negative properties here, all positive properties here. Now, using this, you can answer a host of questions. But look at this question first to start with. You understand my question properly. Between sulfur and chlorine, which is a metal? I repeat. Between sulfur and chlorine, which is a metal? In fact, none of them is a metal. Neither sulfur is a metal nor chlorine is a metal. Both are non-metals. Therefore, if you strictly ask me which of them is a metal, none is a metal. But what can you say about sulfur? Sulfur being towards the left side of the periodic table, sulfur is more metallic than chlorine. You can at least see one fundamental difference. Sulfur is a powder, chlorine is a gas. Powder, that hardness, that strengthening nature is one of the properties of metals. Now, so I have never said elements which are on the left are metals, right are non-metals. I only say elements towards the left are more metallic, more electropositive and better reducing agents than those who are on the right side. Now, magnesium, aluminium, silicon, sodium, all these belong to the third period of the periodic table. Magnesium, aluminum, silicon, sodium. If I ask you which of the following is highly electropositive, more electropositive, and don't tell me towards the left magnesium. Of course, magnesium is left here, but this is not the order you have to use. You have to follow the periodic order. First, arrange them in the periodic order. Sodium, magnesium, aluminum, silicon, atomic numbers 11, 12, 13, 14. So, now you can say using left-right notation. Now, most electropositive sodium, most electronegative silicon, like this. Okay? And which of the following is the best reducing agent? Left, whichever is towards the left, sodium. Which oxide is most acidic among them? Sodium oxide, magnesium oxide, aluminum oxide, silicon dioxide. Which is most acidic? Towards the right, oxides are more. Towards the right, oxides are more acidic. Therefore, silicon dioxide is most acidic. Now, let us look at the host of this. Na2O, MgO, sodium oxide, magnesium oxide, aluminum oxide, silicon dioxide, P4O10, SO3, Cl2O7. What is there? What is common among them? All of them belong to the third period. 11, 12, 13, 14, 15, 16, 17. All of them belong to the third period and all of them are in their highest oxidation state. Sodium here is in +1 state. First group +1, second group +2. Aluminum is in +3, +4, +5, +6, +7. What is it I have taken? Oxides in their highest oxidation states of the third period, because there are other oxides SO2, Cl2O6, P4O6, but I am not comparing them. I have taken oxides in their highest oxidation state. Now, what can you say about Na2O? What you can say about Na2O is highly basic. Highly basic. Sodium oxide is highly basic. Magnesium oxide, basic. Just basic. Al2O3 is amphoteric. What do you mean by amphoteric? Both acidic and basic in properties. It has some acidic and basic properties, amphoteric. It can react with both acids and bases to form salts. It can react with both acids and... Okay. What about SiO2? It is weakly acidic. It is a very weak acid. It produces a very weak acid. Weakly acidic, acidic, highly acidic, SO3 is highly acidic, and Cl2O3 is very highly acidic. So what is that you observe? Once again, left to right, the acidity of oxides is increasing. Na2O, MgO, Al2O3, like that. So that's how we can compare trends in electropositivity, metallic character. And what about electronegativity? Electronegativity is the tendency to attract shared pair of electrons. Electronegativity is the tendency to attract shared pair of electrons. Therefore, it is opposite nature to electropositivity, readiness to lose electrons. Now, NH3, PH3, ASH3, SBH3, BiH3. Which is most basic? Nitrogen, phosphorus, arsenic, antimony, bismuth, all of them belong to the same group. Which is most basic? You may be tempted to use this minus plus logic. What is that? Towards the top, electronegative, towards the bottom, electropositive. Minus means acidic, plus means, we have already discussed that plus minus minus plus thing. Okay, but don't forget that is for oxides only. That is for oxides only. These are hydrides. The question is about hydrides here. Therefore, you can't use the same logic. That logic is for oxides. Now, N2O5, P2O5, Bi2O5, if formed. Which is most basic? Definitely oxide, bismuth oxide. So, left to right, top to bottom. Now, between F2Cl2Br2I2, among halogens, which is the best oxidizing agent? You just imagine, towards the left they are reducing agents, towards the right they are oxidizing agents, towards the top oxidizing agents. Therefore, best oxidizing agent is fluorine. Okay, top to bottom oxidizing ability decreases. These are the trends in the periodic table.